I'd like to welcome you all to our seminar series of Computational Social Sciences Center at Kochi University. Today, we have the great pleasure of hosting Dr. Kohei Watanabe from Waseda University, where he will be speaking about a really interesting topic, neural latent semantic scaling, polarity analysis based on microlanguage models. With that, but before I give the floor to Dr. Watanabe, I'd like to introduce him briefly to you. Dr. Watanabe is a computational social scientist specializing in textual data analysis and text as data methods. He's currently based in Japan, where he works as a senior data scientist at Laser Asset Management. In his role, he leads the development of analytical pipelines for large-scale analysis of economic news, financial reports, and corporate earnings call transcripts across the US, Japan, and Europe, working directly with original language texts. His research focuses on developing semi-supervised machine learning approaches to extract substantively meaningful dimensions from large text corpora, such as business uncertainty and environmental impact. He's particularly well known for his work on methods like latent semantic scaling and seeded LDA, which enable the analysis of millions of documents in a scalable way without relying on predefined dictionaries or off-the-shelf pre-trained models. Dr. Watanabe received his PhD in social research methodology from the London School of Economics and Political Science and his MA degree in political science from Central European University. He's affiliated with Waseda University as well as LSE as a visiting scholar. We're happy to have him with us today and very much look forward to his talk. The floor is yours.
Thank you very much. It's a very, kind and detailed introduction of me. I'm very happy to be here. I never been to Kochi University, but I've been to Turkey multiple times, and it's a fascinating country, like very exciting, always. I would love to visit your university one day. The campus looks very beautiful, and there are a lot of interesting people over there. Um, Okay. So I'm a methodologist, not completely a data scientist or computer scientist. That basically means I do some social research. I was political scientist, and I'm still a political scientist actually, but I'm a little bit into finance, for my day job at the asset management company. And the problem that we have as a social researcher is that we don't have a good data set to train models, especially in the textual data. As you know, in order to do some uh, automated analysis of textual data, you need to have nice data set to train model on. But it's quite often not the case. So how do we live in that kind of situation? That's underlying problem I'm trying to address through my research. And one of the tools is seeded LDA. That's that's what we call semi-supervised algorithm. We just not only applying a model to a data set, but also we can kind of guide how models to work. And another type of algorithm is latent semantic scaling that I developed a while ago for my as part of my PhD degree, and that also the way to address that problem. And this is what I want to talk about today. And the title of my slide is neural latent semantic scaling. This is a little bit, I tried to make it a little bit catchy because people are talking about neural network all the time. But please bear in mind that this is not really a large language model or deep learning kind of research, more like a way to like methodological research. So let me start. Uh, So what is linear semantic scaling? This is probably what I should explain first because only some of you might have used this. And this is methodology that I proposed in a paper in 2021. But this has been used in my project even earlier than that. And if you look at the list of applications below, uh, there are papers from like 2017. So it has been used by the time the paper was published. And the advantage of this method is that no, as a social researcher, as a political scientist, we want to study a concept, to capture a concept that is very, very unique to the domain or the theory we are trying to develop. And in computer science, for example, people study like sentiment, positive, negative, very generic. But social scientists are more interested in more specific dimensions, such as political rallies as freedom of expression or social disorder. That's very, very specific in that context. And also, or reconciliation or versus sectarianism, or hero versus villain, or propagandist versus watchdog, emotionality versus factuality, democratization versus backsliding. So those very, very specific concepts need to be measured in social research. And also, we want to study language, different languages. I applied this method to Russian. Some other people apply this to Arabic or Chinese or even Serbian. And recently, Seki-san, Lunta, is in this seminar, published an interesting article analyzing um, Turkish text. So the point here is that we want to analyze something very, very specific in a target language. And how do we do that? So the algorithm of LSS is actually very, very simple. So this is essentially what the people call latent semantic analysis with cosine similarity computation of the computation by computing similarity between words and seed words. And in this algorithm, we apply SVD, singular value decomposition of the document feature matrix, and get a nice low dimensional representation of the matrix. Then we compute similarity, cosine similarity between words. And we choose seed words manually. The examples of seed words are here. The positive seed words are good, nice, excellent, positive, fortunate, correct, superior. Negative seed words, bad, nasty, poor, negative, unfortunate, wrong, inferior. So these are the commonly used seed words created by computational linguist in 2003. So if we compute cosine similarity to those seed words, we can assign a positivity score, negativity score to all the words in the corpus. So that's the idea. Then once we compute the similarity scores to all the words in the corpus, we can give weighted average of those polarity scores to the document in the corpus. Then we get document polarity scores. So this is how it works. But as I use this method, I came to realize that there are a couple of problems in this algorithm. The first problem is that it's hard to interpret the polarity scores. Now it is cosine similarity, but yeah, if I say this word has zero point 0.1 score, but yeah, it's just a cosine similarity, no substantive meaning there. And second problem is that the scores are only comparable within the same corpus. If I fit separate models to separate corpora, then probability scores are not comparable. And third, the highest probability score, very positive but very negative scores are given to seed words themselves. We already know that they are highly polarized, but our aim is discovering words that are equally or even more polarized than the seed words. And the fourth problem is that the quality scores can be negative, even if we have only positive seed words because of the nature of the SVD and cosine similarity scores. So these problems makes application of this method, LSS, difficult in certain settings. And then I started thinking, what can I do? How can I solve those problems? Then I started thinking about using language models. And if I use language models, no, we can probably solve all those problems because it's probabilistic, not based on cosine similarity, but not scores are based on probabilities. Then they have very different distributions. And these days, people are developing and discussing various language models, like from very small to very large, as you know. And if I use small or micro language models to predict the probability of occurrence of seed words in certain context, then in the documents that I want to assign quality scores, we can do the same thing, same kind of analysis as LSS. And so in this research, I'm mainly focusing on very small language models because we don't usually have large corpora to train large or even middle-sized language models. And also, we want to capture domain and time-specific relationship between words. I think you will understand what I mean here. Anyhow, the language model I tested for neural semantic scaling is Watanabe. It's very old, but because it is old, we know how it works, and I also implemented that in my package, so it's very easy for me to study. This is how Watanabe is represented in diagram, and Watanabe is one of the masked language model that predict the occurrence of words. So if for example, if word I occurs, then what the words occurring around this word I, then it will there are two models, one is called skipgram and another is continuous backward words. And the skipgram model predicts words five words before and after the word, the current word, the word I. And the probability of the occurrence is predicted based on the this projection layer. And projection layer is used to predict those surrounding words. In order to train current word, it will go through from 5 words before to 5 words after the current, and including the current word itself. And by doing this, we can get so-called word vectors. And word to vec is, as the name suggests, the algorithm to create word vectors. So people can compute cosine similarity between words, then get synonyms. That's a typical way of using this. But what I'm interested in is actually not only this word vector V, the matrix V, but also this W, the weight given to the word vector, so that we can get the probability of those occurrence of words. And so people have been using this V matrix for various purposes, but very few people have really used this W matrix, and this is partially why I need to develop my package for What2Vec. I didn't find any package that allows me to extract and use this weight to predict the probabilities. The another algorithm called continuous backwards is very similar, but different in that the probability is computed based on multiple words, a combination of multiple words around the current words. So it's just a mirror image of the skipgram almost, but the structure is the same. So we get word vectors, B matrix, by trying to predict the current words using the combination of the surrounding words, then multiply that by the weight, then get the probability for the current word. So having that in your mind, let's look at this spatial polarity score equation. So this V is a k-length word vector. So k tend to be like 200 to 300 in sentiment analysis. Then the length of word vector can be the word vector can be created using SVD or Word2Vec, or any matrix factorization method. Then compute the cosine similarity between V1 and Vm. Then weight the cosine similarity by the polarity of the seed word, the PM. Then take the average of that. Then we get the polarity of word GI. So that's it. Very simple. But if we wanted to compute probabilistic polarity, we have a little bit different the equation here. So this is the word vector. But this word vector needs to be weighted by the W, the weight that people haven't been using explicitly in research. Then we get the this EIM. Then this EIM is given to the activation function, the sigmoid function. Then it's gonna be the probability ranging from 0 to 1, and that probability should be weighted by the polarity of the seed word. Then we get the polarity of the words for all the word I. Essentially the same, all the words in the corpus. So these are the difference. The point here is, we use this V and W in this case. And the document polarity. The document polarity is computed in the same way at the moment for spatial and probabilistic approaches. Simply weight the polarity scores or words, GI, by the normalized frequency of word in each document. Then we get estimated polarity of document y hat. Yeah. Then yeah, I compared how those different methods behave using the same data set I used in the original LSS article. And for that, I collected 33,000 New York Times economic news articles, and classified, well, actually not classified, scaled, what we call scaling, gave continuous scores to 450 manually annotated articles. And these articles are annotated by even earlier researchers, Yang and Shoroka. They created lexical the sentiment dictionary. It's a large dictionary, and they tested that dictionary using that annotated news. So I tested a spatial LSF and also a probabilistic or neural LSF and dictionary. And that dictionary, LSD, lexical sentiment dictionary, is very large and very well made. In total, it has like 4,000 words, more than 4,000 words, negative words and positive words. And spatial LSF are three types based on not LSA, sorry, LSA and Shibor and skipgram. And probabilistic LSS is only Shibor and skipgram. And the conditions are different vocabulary size that apply only to dictionary, and different dimensions, the length of word vectors, and also the size of window. This is only applied to the word to vec. Then this is the result. So if we look at spatial one first, then we notice that skipgram. So this is a skipgram based LSS. So this is spatial. So the cosine similarity are computed based on the word vectors created using skipgram model, performed quite well. But continuous backward words didn't perform that good. It's about the same as the SVD, the classic LSS. Then what we want to compare these with is actually dictionary, because LSS is created to replace the dictionary-based method. And dictionary on the left vary quite a lot, because if you downsample the data size of the dictionary, the performance of the dictionary become really low. So in other words, in order to get a nice result, you have to have thousands of words. Whereas we only need several seed words, like 10 or 12 seed words for LSS. And so on the left, there is both continuous backwards and skipgram models too. And these are what I was most interested in. I wanted to test here. And interestingly, skipgram didn't perform as good as spatial counterpart for some reason. But continuous backwards actually sometimes performed better than uh, any other approaches. Then I started wondering why this happened. Um, Before going um, to the further explanation, the difference between those models, let me show you what I meant earlier. The polarity of words are those. If you look at SVD, the polarity scores are 2.52, the highest. That's actually the seed word, right? So no surprise because we knew that this is positive word. And if you look at other words in the column, you see very uh, idiosyncratic words, something hard to make sense of. It's probably a kind of overfitting to the data. But if you look at spatial Wattbeck, spatial LSS based on Wattbeck, you see a lot of seed words too. But there are nice words that are not in the seed word, like sparve is a good word, I think. And but if you look at the Wattbeck LSS based on probabilistic LSS based on Wattbeck, it's probably even better because we don't see many seed words in this list. We see excellent somewhere in lower part of the list, and polarity scores are quite high for for the highest word, most strongly polarized words like position, virtue, prestigious. These are, I think, genuinely positive words that we expect to see here, and fewer idiosyncratic words that are hard to understand. And when it comes to negative words, the same pattern can be found. SVD, the polarity score, so biggest negative polarity scores are only minus 0.4, minus 0.148, and a lot of idiosyncratic words. And also spatial LSS based on Wattbeck has seed word here and seed word here, nasty and long. Then there are some other negative words, but not so, the scores are not so big. Then again, if we look at probabilistic LSS based on Wattbeck, we see minus 0.8, a lot bigger than other scores. Then we also don't see any seed word here. So those words are discovered by the algorithm automatically. So this is what we want to see. And we also see the distribution of the scores. And if we assign polarity scores to documents and compare with manually assigned scores ranging from -2 to +2, then the most positive documents are not as positive as it should be. It's about the same as this the second most positive document category. So we use a bent at the top. And also, the special LSS based on Wattbeck has a bent at the bottom. So some of the documents should be a lot more negative, but the algorithm failed to recognize that. These two cases are probably because of the inability to find very, very polarized words, very negative or very positive words. The probabilistic one, probabilistic LSS, based on Watanabe, has a very clean linear correlation between those, between correlation with human coding. This is what we want to see. And then, in order to understand why those algorithms behave differently, I started computing perplexity. This is something that people use to evaluate models in machine learning. And here, I didn't compute compute how accurately the model can predict the occurrence of all the words, but only seed words, because we are interested in how accurately the model can uh, predict polarized words, not generic words. So this is a equation of the perplexity, and the key is just you know, take a product of this observed frequency and the log of the predicted probability. Then, if because of this minus, the perplexity score should go small when the model is performing well. And so this is what I got by comparing the perplexity and the correlation. So if the scores are higher, then it shows great agreement with manual coding. That is good. But yeah, as the perplexity goes down to the left, then the correlation coefficient goes up. So this is what I wanted to see. And in continuous backwards model, the scores can actually reach 0.35, a lot higher than a skipgram model. And my interest was why this region is so high compared to other cases. Then I computed with the different parameters, and I noticed that the perplexity for Shibo context backward was actually goes down quickly as the size of the window becomes bigger. Then around 30 words, that is roughly 3 times larger than what people use, then the perplexity score is almost minimized. So it seems that for this particular application, larger window seems to be desirable. And so you might be interested in how I use this method. I and other social scientists use this method. And here's an example. So I've been analyzing international news using this new type of LSF to create a geopolitical threat index. And unlike sentiment analysis, the seed words are only these. So they are all not, they don't have numeric weights. This is what we call unipolar, no scores for negative side. And if we have negative scores in this case, we are kind of screwed up because we have no way to interpret what the negative scores. But Watanabe-based LSS does not produce any negative scores, so we are good. And we combine the polarity score, the threat score in this case, with topic analysis by LDA and geographic classification using NewsMap. And we train those models over 3 month rolling window. So there are a lot of models on the temporary local data set. Over 50 years in the case of United States newspapers. These are the seed words, no, sorry, polarity words according to the model trained uh, in early 2022. And if you look at the highlighted words, then I think they are very intuitively positioned, very scary words and attack, feared, extremism. But if you look at the left, um, you don't see anything in the negative region. That's what we wanted to achieve, so that we can literally substitute like word count, dictionary-based word count with these probabilistic scores. No other way to represent the data, that the parameters of the model is that highlight the country names in the corpus, and you see Ukraine, Russia. This is the time when the war started. Have very high polarity scores and also high in frequency. Taiwan, and Moscow, Iran, and I think these are they're pretty intuitive. And yeah, Turkey here, and yeah, because there are a lot of things happening around in that region. And then we can, if we combine geographic analysis, topic analysis, and polarity analysis, we can create a index, a geopolitical threat index like this. For example, we have China here, and China's security threat score has gone up in around 2020. And Russia's score apparently went up from 2021 to 2022. It's preceding the Ukraine invasion a little bit. That's interesting. So I think I'm running out of time. Then here's a conclusion. So Wattbeck is a very small. This is micro-language model and very old, but I think the result is promising. At least it has the properties that I wanted to have in LSF. No, these are like the range of polarity scores are wider than other methods, and the polarity was more intuitive and easier to understand. And and good news is that there are a lot of language models that we can use for this. We can further develop a tool based on the recent development in the field, so that we can probably capture more complex expressions like negation, irony. Those kinds of things were difficult to capture in the old text analysis methods. And if you are interested in using this method, the package is already there. I've been maintaining the LSX package to do this. So please just download from Clan and test it. If you have no question, I'm more than happy to answer over the email or just after this presentation. And yeah, thank you very much.
Thank you so much for this really thought-provoking presentation. So I will open the floor for questions or comments our audience may have. If it's easier, you can unmute yourself and ask, but you can also type in the chat box. I can read it out loud. I usually give some extra time to our audience to prepare their questions. So in the meantime, maybe I can ask some of the questions I have in mind, if that's all right with you. So about the failure mode, what is the clearest failure mode of LSS compared to dictionaries and supervised models? Because you argue that LSS is flexible and cost efficient, but also less robust than dictionaries and noisier on short documents, right? What kinds of corpora or tasks should people avoid LSS for?
I think the question is, what's the advantage of using LSS versus dictionary? Um, for example, if you want to analyze those concepts, like freedom disorder, right? Reconciliation, sectarianism, you would probably don't find any dictionary. No one really created it. So you either make dictionary or like at least hundreds of words.
Mm-hmm.
Then you might want to expand the like 10 or 20 words using a method like LSS. LSS only needs like 10 or 20 words to get about about the same result as dictionary.
Mm-hmm. Thank you.
And I think social research especially, people need to test new hypotheses, focusing on the different concepts. That by default means there's no lexical resource, list of what keywords that you can use. So in order to be a cutting edge of the theoretical development, it's probably better to better not to use existing dictionary. That's the kind of thinking we have.
Thank you. Um, and it appears that LSS is in a way explicitly linear and maybe naive about interactions. Do you have any recommendation or workaround for negation heavy genres like sarcasm or
Hmm.
editorials?
Yeah, that's the problem. The negation, uh, yeah, can be, I think, dealt with by training, um, yeah, let's say or Wattbeck on the subset of corpus that doesn't include negation expressions, for example. And that's one way, but it doesn't really capture the dependency structure of words. That's why I think we should start using more sophisticated language model. Then, yeah, I think it can.
Mm-hmm. Yeah. Because I mean, also comparability across languages without translation is a really big promise. But if corporate different in genre, style, I don't know, journalistic conventions, um, the question then becomes, are the resulting scales truly comparable? Like what diagnostics would you run before making cross-country claims for researchers using it?
Mhm. Yeah. Um, yeah, cross-lingual analysis is quite challenging and also interesting. And yeah, if we Wattbeck already can do some kind of transfer learning, but yeah, if we yeah use more sophisticated algorithms, probably result to be more comparable across language. That's my kind of naive hope.
Mm. Yeah. Um, I mean, LSS is really, I guess, presented mainly as unidimensional, and in other real projects, users often want multi-dimensions like threat versus empathy, legalism versus moralism. What is the cleanest way to do this without dimensions in a way bleeding into each other? I'm asking this specifically because we do have some of our students here working on their master's theses, which would very much benefit from this.
You mean the how to measure things, very clearly towards the either extremes.
Mm-hmm.
Um, yeah, if you look at the distribution of LSS scores, now it looks like a normal distribution. There are a lot of scores concentrated, around zero in the middle. That's the region you have to be careful, right? And that basically means you cannot really tell this is black or white. And then what I usually do is that I just take was documents with high polarity scores, like if it is normally distributed, then it's gonna be like greater than 2, +2 or -2. Then yeah, don't yeah include documents between -2 and 2 because they are kind of uncertain. This causes a lot of false negatives, but probably you can draw a same kind of conclusion. Yeah, as without a lot of false negatives, I think. So yeah, I usually say to people using text analysis, no, it's a crude method and also the game of big numbers. So it is if you have a lot of documents, then you finally, if you aggregate those scores, then you get the truth behind the numbers.
Um, and again, this is for our students in a way who are a little shy today for some reason. They're not typing their questions, but again, I'm giving them some extra minutes to do that. In a student project, what would be the clearest signal that LSS is a bad choice of a method? Is it really the document length, corpus size? I don't know, maybe instability or concept ambiguity, that should, in a way, maybe stop them from using it.
Hmm. Um, I think sometimes the seed was so infrequent and not enough information to the algorithm, then it fails. That's one case. Another case is the corpus itself is just too small. I think there are two cases. The first one is the concept is too specific, or it was not good. And the other problem is the data is not enough, which is more difficult to solve. But as a diagnosis, the polarity squads, distribution polarity squads, like this, actually help us to understand. So it has a nice distribution from right to left. And this extreme region is also populated by many words. But when it is not working very well, you see only very few words in the extreme, and a lot of words are concentrated around low region. Then um, yeah, it's not this is an indication that the algorithm is failing to assign scores to no, many words based on the feed words. That's basically the failure. Yeah, in this case, it doesn't work.
Thank you so much.
Can I ask a
And
question?
sure,
Sorry.
absolutely, yes.
I mean, I'm sorry, I don't want to interrupt you, but
Go ahead, Lungta.
yeah, thank you, Watanabe Sensei, for this seminar, and thank you for sparing your precious time. I actually was not aware that you present this word-to-vec based LSS method that allow researchers to measure just one dimension, not needless, and doesn't have to be in a different to plurality, which is very promising because I thought about because try to, for example, in the past, measure sort of populist rhetoric from President Erdogan's speeches, But I was not sure what is the different dimension from populism rhetoric versus something else. And then I was a bit struggling with finding the seed word. But I think so my question is, can this kind of like populist trick measurement is can we apply to measure this kind of the trick by using word-to-vec based LSS?
Yeah, actually, we had seed words for seed words for opposite of threat, secure. So we started with bipolar LSS. One side is threat, another side is secure. But it didn't work very well. Yeah, this one-sided unipolar analysis produced more intuitively. So that's why we are doing this. And also in some cases, you cannot really argue that two concepts are opposite, complete opposite. Sometimes secure, for example, and threat can go high simultaneously. No, yeah, it's a like mathematical question maybe, but no, you cannot really assume the things have complete trade-off between those two, and so it might be better to have multiple unipolar like two unipolar scales instead of one bipolar scales in order to capture complex things like populism. And then you can probably combine those two scores harmonic mean or something like that. Then if those two anti-elitism and maybe some nationalism both goes up, then it's a not typical populist nowadays or something like that. So in order to do that, in order to compute harmonic mean, for example, you shouldn't have negative scores, right? So yeah, you can try it. Yeah, please try and let me know how it works.
Okay, I'll give it a try. Thanks so much for that. And I mean, if nobody would, I have another a bit more technical question, which is, this example that you were just very much like showing right now. So these seed words for thread, how did you end up selecting all these seed words? Like where to start? How do you kind of filtering out, filtering in, or kind of? I think because as I have used LSS, there are a lot of, going back and forth. Oh, this didn't work. Maybe I should drop this one, and then maybe I should add this one, etc. Could you exemplify for this one a bit more?
Yeah, that's always yeah, it's always a question how to make a list of good seed words. Yeah, first I just collect many words that can be used as seed words. And for that, thesaurus, for example, like general thesaurus is useful. I just try to find what the same, word with same meaning for like threat, then come up with aggression, then get aggressive. Then in this way, I can snowball words using the thesaurus. But of course, there's a risk of including something that you shouldn't have. Then in order to define or create a final list of seed words from the longer list, I just check one by one. And if I see some words that are not I'm expecting to see, if some of the potential seed words gave high quality scores to something I don't understand really, it's not so intuitive, then it is causing some kind of a false positive cases. And then okay, let's not include that because it's more harmful than beneficial. So that's kind of approach I'm taking.
So another point is that you didn't use the asterisk wildcard. this specific seed word, right?
Mm-hmm.
But could use actually. But maybe for example, aggressive can be aggress, so that can incorporate aggressions, or I don't know, etc. Like harm can be like white card harmful, etc. But you did not do it this time,
Mm-hmm.
or
Yeah.
any specific reason.
Yeah, it's a little bit risky to use asterisk, like wild card, because there might be some word that I don't know in the corpus that causes a lot of matches, false matches. Then I don't use unless it's necessary. And I thought I have enough seed words here. Then I didn't. That's the only reason why.
Thank you.
If you don't have any other questions, I'd like to thank you very much again, Dr. Watanabe, for this really inspirational presentation. And I also would like to give the last words to you if you wanted to add anything before we conclude the session for today.
Thank you very much. I hope you find this kind of semi-supervised method interesting and useful for your research. I don't know, which orientation, like what kind of orientation you have, more like computer scientist or social scientist. But if you're a computer scientist, please help me developing, language model implementation. If you are a social scientist, please use this to do some cool research, like Lunta does. So thank you very much.
Thank you so much. I'm sure a lot of our students actually will benefit from it. And with that, I'll pause the recording.